do without metrics. Then another reason I very often hear from people why they don't use metrics, yeah, first of all, I don't know the metrics, and also I'm not aware of any tools that measure those metrics for me. And at least if you're working in the area of Java, C# or Python, there are free tools out there like Sonograph Explorer. They're completely free, even for commercial use. And they measure most of the metrics that you will learn today. So you can actually get those metrics out of your software system, and you can even run those tools in your build to automatically measure those metrics. So that's what we recommend, that you measure metrics and rules in your CI builds so that you are able to detect harmful trends early enough. And then, of course, as soon as you have metrics, you can use them to trigger events in your build. For example, if a metric goes under a certain value, you could break your build and say, hey, we need to do something about that metric. Metrics are also great for quality gates. Quality gates are basically a set of conditions that says when is your build green or when is it red. So you could, for example, say in my company, my build breaks if somebody introduces a package cycle or an architecture violation. Those are the deadly sins that we do not allow. But we also could add rules, for example, to say we don't want any new to-do statements in our code. That could be one rule, or we want a certain metric to be under or over a certain value. All these things could be entered into quality gates, and quality gates could be based on the current state of your software or the comparison to a previous state. For example, you could say, I don't want to get worse than my last version of my software system, so that would be a valid condition for a quality gate. Also, some metrics are really excellent architectural fitness functions. I don't know if you're aware of this, but this is basically there are books out there which talk about the architectural fitness function. I'm just trying to figure out which title that was. Just a second. Yeah. All good. There's one book I can recommend. It's called Building Evolutionary Architecture by Neil Ford, Rebecca Parsons, and Patrick Coor. They introduce the concept of architectural fitness functions, and they're really excellent because if you build a software architecture, you build it to achieve certain goals, for example, maintainability or scalability or things like that. And if scalability is one of your goals, you also need metrics to measure if your system achieved scalability. And then in that case, we would call that an architectural fitness function. Another very good reason to think about software metrics and measuring quality is the fact that just in the US alone in 2020, we lost about $2 trillion caused by bad or poor software quality. So you can read that report actually, and it's a mind-boggling number. It's about 10% of GDP lost by bad software quality. And if you look at the report, very interesting finding, for example, 260 billion alone coming from unsuccessful IT projects. The principle of technical debt is estimated to be $1.3 trillion. Legacy systems extra cost of 520 billion, operational failures 1.56 trillion. It's enormous, yeah. Just think about little disasters like, for example, the Boeing 737 MAX disaster, which almost killed the Boeing company. Enormous cost because they took some shortcuts in software developments. So those little shortcuts where you assume to save some cost can cost you a lot more later, especially if you're working on software systems that are critical for the survival of human beings. And of course, avionics systems in an airplane are very critical. They have to be done right, otherwise the plane will fall off the sky and people will die. So what are the findings of this report? So one interesting finding is that failed project went up 46% compared to 2018. That's interesting. Should this go down? So I think we're developing software for 60, 70 years now, and we still haven't learned how to do it right. And we still have a relatively high project failure rate. So that's interesting. How did that happen? What changed dramatically since 2018, or I would say almost since 2015. My suspicion is that many companies jump on the microservices train without knowing what they're getting into. Microservices have their reason for existing, but in most cases, I'm pretty convinced that you don't need microservices, where companies are jumping on microservices right now. And what you get with microservices, you don't do it right, and doing them right is really hard, is you go from a big ball of mud to a distributed big ball of mud. I'd rather be with a big ball of mud, because a distributed big ball of mud is one level of hell deeper than the normal big ball of mud. Yeah, legacy systems problems contributed 520 billion, and some key recommendations are: ensure early and regular analysis of source code to detect violations, weaknesses, and vulnerabilities. That's a very strong argument to use static analysis tools. That's exactly what static analysis tools are doing for you. Measure structural quality characteristics. So that's why you need metrics. And also recognize the inherent difficulties of developing software that use effective tools to help deal with those difficulties. It is time that we recognize how difficult software development is, how difficult it is to achieve a good result, especially if many people are working on the same piece of software, and impose some stricter rules and regulations to guarantee a good outcome. Because many times, so if you're really lucky, people are doing code reviews for commits, so that's a good thing already, but it's not the whole story. They can't be perfect. You need to measure your stuff. You need to have comparable numbers to see if you're moving into the right direction or not. So then why nobody is using metrics? First of all, people don't know the tools, and many also don't know the metrics. In many schools where you learn programming, where you learn computer science, they're still having not a lot of curriculums about software metrics and tools associated with them. And then, of course, often a single metric does not tell the whole story. You need to look at software from different angles, and we'll have some good examples of this in this talk here. And then, of course, who has time for this? Because we're working in an industry where everybody's permanently under stress and time pressure. One of the reasons why we're under so much time pressure, of course, is a big ball of mud, which makes every change more difficult. If you're working on a big ball of mud, and usually if I go to conferences and have this talk, I ask who is currently working on a big ball of mud, about 70 to 80% of all hands go up. So I know what I'm talking about. Then everything becomes more difficult, and every change becomes more or less a little nightmare. Of course, another thing, and I hate that I have to write this down, metrics, of course, are only useful when they also trigger actions. If you just measure the metrics but don't do anything about it, it won't help either. And you might say, yeah, that's obvious. Why would anybody say that? But another thing from the talks on the conference, when I say, okay, there's a nice tool out there called SonarQube, which at least does some basic static analysis on your code and finds some bugs in your code, which is always good. And then I'm usually asking, how many of you are using SonarQube? And about 50% of hands go up. Yeah? And then say, who actually looks at the results of SonarQube and does something about it? Then only 25% of hands go up. Yeah, so that tells you the story. Just running the tool in the background and not doing anything about the results is also not really very helpful. But of course, why would not anybody do nothing about the results? Because they don't have time, they're under time pressure and have other problems to solve. And of course, so many possible metrics. So I hope I can at least give you some ideas about what you could use, what you should use. Now, this is a dependency graph rendered with SonarGraph Explorer. That's a so-called cycle groups, and it's from Apache Cassandra version 2. It's a very old version. It just got much worse since then, but that's the beginning. You see about 50 Java packages in a cyclical dependency. I mean, you can get from every package to any other package and back another way. Yeah? So they're so tightly coupled that you just as well could put all these classes in one single package, and that would actually be the right thing to do. But then you have a package with something like 3,000 Java files in it. Packages should be used to organize your code in a way that you build something like a hierarchy of packages. But of course, in many software systems, this ends up as a big cycle, which basically where you lose the organizational benefits of packages. It looks interesting, right? Like a piece of art or like some image from a particle collider where you just shoot some atoms on each other and the splinters fly everywhere. There's two metrics that back up the fact that this is not good. Maintainability level, ML, is at 9% for that software system. 9% of a possible 100%. 100% would be the perfect score. 0 would be the worst possible score. And we're pretty close to 0 here. It couldn't get much worse. But of course, over time, let me tell you, it got even worse. Yeah. And then propagation cost is a 62%. That means every change I do to Cassandra affects 62% of all classes in Cassandra directly or indirectly. Means that increases the probability of regression bugs quite dramatically. So we're talking about spaghetti code here. And so how do we measure the spaghettization of code? What are attributes of spaghetti code? High coupling. Many circular dependencies. No clear separation of responsibilities. Means if you want to fix something, if you want to add a new feature, you can't do it in just one place. You have to touch like 97 different places, and chances are will forget at least one of those places. If that sounds familiar to you, I would assume that about 90% of all systems suffer from some variety of this problem. Now, spaghetti code versus clean code. Most code dependency graphs would look like the one on the left here. So you have a lot of crisscross dependencies going all over the place. And an organized piece of code looks like the one on the right here. We have the colors. Those are for the domains, for the functional aspects. And then we have the layers for technical aspects. And we have no circular dependencies. For example, the orange domain can talk to the red domain and the yellow domain, but not vice versa. And of course, layer dependencies can only flow downwards and not upwards. So this is a structure you want to have for your software system. As soon as you have this kind of modularity in your system, if you are able to implement vertical slicing too, instead of just having horizontal layers, this gives you a lot of benefits. One of the benefits would be if for some reason you really need microservices, migrating a software systems like this to microservices would be relatively easy because you can basically translate the different silos, vertical slices, to microservices. Of course, there are lots of advantages. Just let's look at testability. On the right side, I can just test all the packages on the bottom. I can test them without having to know anything about the rest of the system. I can test them independent from the rest of the system. On the right side, I can only test everything together. It's basically impossible to test anything in isolation. Another important aspect are cyber threats. Just think about which software would be easier to harden against cyber threats. My bets would be on the right side because they're the data flowing from the top. It's very easy to know where you need to have your validations and making sure that no bad things can enter your system. On the left side, there might be many side doors, and it's much harder to make sure that that software is actually secure. And last but not least, also code comprehension. Developers spend a lot of their time reading code and very little time writing code. So if your code is easy to read, they spend less time reading code and more time writing code. If your code is hard to understand and tightly coupled, they will spend a lot more time reading code, a lot less time writing code. Statistics actually say that in most projects, developers spend upwards of 80% of their time reading code. So comprehensibility of code is a very, very important productivity factor. Now, which tools could you use for metric gathering? There's all kinds of tools out there. For example, Understand, one of the big advantages of that tool is, unfortunately, it costs about $1,000 per seat, but it supports multiple languages and gives you a couple of interesting metrics. Then we have NDepend for the .NET world. Its commercial is about $300, $400 per seat. Then we have Sonograph Explorer. I think that's very competitive because it's free. Of course, it's also a shameless plug because it's a tool we wrote. You can actually get this from our website. You just have to register on our website, hellotomorrow.com, and then get a free license, which you manually renew once per year, but it's up to now, it's absolutely free. It was free for the last 6-7 years, and at least it will stay free for the foreseeable future. We might change our mind at one day, but not at this point right now. There's another freeware tool called Source Monitor, which also goes over a couple different languages and gives you some basic metrics about your software's tool. So let's start jumping into the metrics themselves. So what are good metrics to measure structural decay? We have average component dependency. I'm going to explain those in detail in a minute. Relative cyclicity with a focus on cyclic dependencies. We have structural depth index, which will tell you how difficult would it be to break up those cycles. And maintainability level is something like an overall score that could also be used as something like an architectural fitness function for maintainability. That's actually quite a powerful metric, which you can use as an early warning indicator. That's something we developed in the last couple of years together with our clients. Let's start with average component dependency. Well, that's a pretty simple metric, basically. What you see here, a couple dependency graphs. So in the dependency, let's assume each of those boxes would be a Java file. Yeah? The arrows are dependencies between Java files, and the numbers are the so-called depend upon values. On the bottom, you have ones because those things only depend on themselves. In the middle here, I get to a 3. It depends on those two other ones and on itself. So that's why you get 3. And on the top, you get a 6 because this one depends on the 5 other ones directly or indirectly and on itself. Now you add up the numbers and you get cumulative component dependency. In that case, the sum would be 15. And then you divide it by the number of boxes and you get average component dependency of 2.5. Means every time, every of those compilation units on average depends on 2.5 compilation units, including itself. In the middle, we just changed the dependency directions in the bottom here. We use the dependency inversion principle according to Robert C. Martin. So by introducing interfaces, you can actually invert directions of dependencies. And here we get a better value already. So the value goes down to 2. On the right side, we can see what happens if you introduce a cyclic dependency. Just this little arrow going up in the middle here lets the value explode to 4.33 of the theoretical maximum of 6. So the value of ACD is always between 1 and the number of nodes that you have. 1 would mean we have n isolated islands with no dependencies. Of course, that's not achievable and that's not desirable either. And 6 means literally everything is depending on everything. Then you can, the problem with this metric is, of course, you need to know how many nodes you have, how many boxes you have to make sense of it. If somebody tells you my ACD is 200, well, that doesn't tell you anything because if that system has 200 compilation units, it would be the worst possible value. But if the system has 10,000 compilation units, it would actually be a pretty good value. So you need to know how many elements you have to make a judgment, and one way to do that would be to divide once more through the number of elements. That would give you a metric relative ACD, which turns out to be the same value as propagation cost. So ACD divided by the number of nodes once more would be propagation cost. That's one way to calculate it. There's different ways to calculate it, and it's a really funny story in the background here because I had RRCD very early in Sonograph. Since the very beginning, we had this metric, but we didn't know about propagation cost, which was invented by Harvard Business Schools around that time. And a couple of years later, I found this paper about propagation costs and said, oh, that's an interesting metric. Let's implement it in Sonograph. And I implemented the metric like described in the paper. And then I was confused because it was always the same value as this relative ACD. Of course, after some deeper digging, I found out I just had discovered the same metric that those people from Harvard had discovered, but in a different way. Now, the low-level metrics that go into it, we already learned about depends upon. So that basically looks at how many people are depending on me directly or indirectly. or no, the other way around, on how many people do I depend directly or indirectly. That depends upon. And you could also invert this metric and say, how many people are using me directly or indirectly? That would be used from. If I look at depends upon and would add up all those numbers for this graph, and then I would add up all those numbers for this graph, I would always get the same sum. So for the same graph, the sum of depends upon and used from must be the same, because one looks at one end of the dependency, the other one looks at the other end of the dependency. Okay, now we can normalize those metrics too. So fan out would be basically on what percentage of our elements do I depend directly or indirectly. And fan in would be what percentage of elements are using me directly or indirectly. Now, propagation cost, as I said, is a percentage value to indicate coupling. Smallest value would be basically 1 divided by n. That's basically the smallest value for ACD is 1. If you divide it by the number of elements, 1 more, that's a possible smallest value for propagation cost. Biggest value, of course, is 100% coupling. And the different ways to calculate it, you can divide ACD by the number of elements, or you can calculate the average fan in or the average fan out value. That would actually give you the same value. Problem with propagation cost a little bit is that it has a little bit of its own life. And basically it becomes harder and harder to keep high coupling the bigger your system gets. Yeah. So for example, if you start with 1,000 compilation units and you really have 100% propagation cost, that means everything depends on everything. Now you grow your system to 10,000 units, and let's assume you don't add any more additional coupling, and then suddenly if your propagation cost, if your average component dependency is still at 1,000, your propagation cost would go from 100% to 10%. That still means that you have a 10% value, but in that case, it would be still bad because you have 1,000 very tightly coupled units. Just by adding more compilation units was a little bit diluted. That's why you have to take this metric sometimes with a grain of salt, and still useful to know how many compilation units you have to get a comparison, because 10%, if you have 100 compilation units and your propagation cost is 10%, it's an excellent value. But if you have 10,000 compilation units, your value is 10%, it's a little bit more concerning. Yeah, the reason why it usually shrinks with system size is because you could also think about a big dependency matrix for your system. And if you had a dependency matrix, you would have the same number of columns and the same number of lines in this matrix as you have compilation units. So if you have 10 compilation units, the number of cells in your matrix would be 100, 10 times 10. But if you have 1,000 compilation units, the number of cells in your matrix is already 1 million. So it grows with the square number of cells. And that explains why usually, even if you don't do much to improve coupling, if you just add new compilation units, usually the value might shrink a little bit. Talking a lot of cyclic dependencies. So one of the concepts you need to understand about cycles is the concept of a cyclic group. A cyclic group is basically a smallest unit in a graph that cannot be further reduced. So here in this graph, we have two cyclic groups, the red one and the gray one. The white one is not, the white nodes are not cyclic, are not involved in any cyclic dependencies. And those cyclic groups are basically the clusters in the system. If you do a graph analysis of the dependency of your system, you can basically reduce the graph until only cyclic groups are left. It would be a topic for another talk to explain why cyclic dependencies are bad, but they have lots of negative connotations. They make code understanding harder, they make testing harder. A lot of disadvantages coming from those cyclic dependencies. So it's always a good idea to keep those cyclic groups. If you can't avoid them, keep them as small as possible. Cyclic groups of 2 or 3 elements are not a big problem, but it's usually they grow over time, and suddenly, like in the latest version of Apache Cassandra, we have a cycle group comprising 1,350 Java files in one single cycle. So that's definitely out of control. So as I said, they make code harder to understand. Testing becomes harder. Modularization becomes more difficult. You increase coupling. And I generally recommend that you should avoid cycle groups with more than 5 elements. That's always a good idea. If they go over 5, just try to break them. And you can always break cycles. We have another training for that particular purpose, which just like how to break cycles. Unfortunately, people don't learn that in school, but one of the basic techniques would be the dependency inversion principles, according to Robert Martin. Introducing an interface to invert the direction of the dependency, that always helps, but there are also other techniques like flow motion and demotion and so on. I don't have the time to get into that right now. That would be a topic for another talk. Also, another thing that becomes more difficult is reuse. Yeah, because if you want to reuse that beautiful class, and then you find out if you pull on that class, another 1,000 classes come behind it, then you might be not as interested in reusing it anymore. And high coupling makes it very, very difficult to reuse classes. Then another kind of cycles are even worse. I would say namespace or package cycles are even worse than compilation unit cycles, because they basically invalidate the package concept that basically says, builds a hierarchy of packages and different parts of software. As soon as you get a package cycle, you can just as well give up using packages and put everything in one package. Now, how do you measure cycles? The different metrics for it, for example, one start metric would be the number of cycle groups and the biggest cycle group size. So that's, if I do a software assessment, which is one of my major consulting activities, I look at the biggest cycle group number first. So that's one of the first metrics I look at, because if I know you have a cycle group comprising 950 elements, I know you're in trouble. You probably know it too, but I can quantify the amount of trouble you're in. Then we can measure cyclicity and relative cyclicity. I'm going to explain this in a second. And we also can measure how difficult would it be to break up the cycles. That would be structural depth index. Now let's start with cyclicity. Cyclicity is a very simple metric. If you have a cycle group of 3 elements, the cyclicity of that cycle group would be 9. It's a square number of the cycle group. If you have 5 elements, it would be 25 and so on. Now you can measure the cyclicity of your whole system by just adding up the cyclicity of all cycle groups. So if you have several cycle groups, you just add up this number, and then you can calculate what we call relative cyclicity. You basically get the square root of the sum of cyclicity divided by the number of elements and multiplied by 100 to get a percentage value. So let's do a little thought experiment about relative cyclicity. Why is this an interesting metric? Let's assume we have a system with 100 Java files. And number 1 is using number 2, number 2 is using number 3, until we come to number 100, which again uses number 1. So in your mind, you should see a big, big cycle wheel comprising all those 100 Java files. In that case, we only have one cycle group in that system. That cycle group has 100 elements. Square number would be 10,000, and the sum of cyclicity would be 10,000 in that case. Get the square root, go back to 100, divide by 100, we'll get 1. In short, we will get 100% relative cyclicity. That's the worst case. Every single element in your system is in one big cycle group. That's the only way you get 100% relative cyclicity. Now, let's assume we have the same system. This time we have 50 cycle groups of 2 elements. Still, you could say 100% of Java files are involved in a cycle, but they're now involved in much smaller cycles. Now let's calculate this. So in that case, we would have 50 cycle groups with a cyclicity of 4. 50 times 4 would be 200. The square root of 200 is about 14. So in that case, we would end up with about 14% relative cyclicity. That shows you why this metric is useful, because the smaller the cycle groups, the better the values. Of course, 0 would be the ideal value, because actually we don't want to have cycles. Sometimes they cannot be avoided, but if you have cycles, keep them small. So So relative cyclicity tells us that this system with a 50 cycle groups of 2 elements is better than the system of one big cycle group of 100 elements. And that can objectively be said, because in that case, in the second case, you can have 50 modules in your systems without having any module cycles. In the first case, you can only have one module. You cannot further cut the software. Now, of course, there's always another side of the coin. In that case, it would be structural depth index. That's a metric we developed, because the interesting question is, if you have all these cycles, is how difficult would it be to break them up? So what are we doing here? We basically run a graph algorithm over those cycle groups and try to find out, find out the minimum numbers of links we need to break to make that thing cycle free. So for each cycle group, we compute how many links do I have to break. And then each link has a weight. For example, if class A is using class B and using 3 functions from class B, then we would have a link weight of 3, because we have 3 different calls from A to B. If we only had 1 call, that would be a link weight of 1. Now what we do at the end, we add up the total number of the total weight of the links we need to break, and then we also multiply the number of links by 10 as an extra factor. So that's what is structural depth index, 10 times the number of links to break, plus total affected lines. Why do we have that special factor in there? Because for each link, you need to figure out, how do I break this link? Do I introduce an interface? Do I move classes around? There are different ways how to break links. So that takes you a little time. That's why we put a weight on that. Then, of course, we add the total affected weight, total affected lines of everything, and we get structural depth index. Now, this is also interesting, because think about our first example, the 100 Java files in one big cycle group. Just imagine, how would you break that? It's very easy. You just need to snip one dependency, and then the whole cycle falls apart. Just need to snip one place. So structural depth index, in that case, one link to break. Let's assume all those links have a weight of 1. Then the smallest possible value in a cyclic system of structural depth index would be 11. Because at least one link needs to be broken, and the minimum weight would be 1. So in that case, it would be 11. Value of 0 mean I don't have any cycles. But it can't be 1, 2, 3, or 5, because this is not a possible value for structural depth index. Can be anything above 11, that's true, but it cannot be anything less than 11 except 0. Now, okay, so in the structural depth index in our first example would be 11. In our second example, if we have 50 cycles and we want to break them all for whatever reason, then our structural depth index would be 550, because we have 50 links that we need to break. Let's assume those links have a weight of 1, that we would have 50 times 11, structural depth index would be 550. So that's an interesting thought experiment, isn't it? Because basically it means, of course, the first case would be worse because we have a very big cycle group, but it's not as bad as it seems because it's easy to break. In the second case, it would be much more work to really get rid of all the smaller cycles. But on the other hand, the smaller the cycle group is, the less need there is to break them up. Cycles of 2 classes are not as critical, especially when they're in the same package. You might just as well leave them there. But if you get those big cycles, those are the ones that create code cancer and basically will eat your system at the end. And again, structural depth index is then added up for modules in the whole system, and you get a total value for your system. And we compute it on component level, package level, namespace level, whatever you want. That is, what do I mean by that? You can have different dependency graph for your system. You can have one dependency graph where you just have dependencies between all your Java files, and that's what we call component level. And then you can have a dependency graph between your packages. Ideally, of course, you don't have package cycles, but in real systems, we see them very often. And then, of course, you can also create the structural depth index for that dependency graph. So basically what we mean with the levels is what is the input for your dependency graph? Is the input single Java files or is the input your package dependency graph? Yeah, let's talk about maintainability level. That's an experimental metric that we developed with one of our customers together, and it's in a pretty good state by now. I don't have the time to go into all the details of it, but just let me give you a quick intro. 100% would be the best possible value. And of course, it should be as close to 100% as possible. Everything above 70% is okay. Everything below 50% is not good. So that's definitely something where you should do something. It is measured per module. So, and then for the system level of maintainability, basically we create a weighted average of your module to find out how your system maintainability is. It should be stable when you don't do major changes to dependency structure, to your architecture and design. It measures decoupling and successful verticalization. Verticalization means you have actually vertical slices in your system. If you do verticalization, like you remember from the dependency graph with the colors, it's a good idea and it reduces overall coupling in your system, and that will give you a lot of benefits. So how do we calculate that? I just give you the simple first iteration of that metric. The first thing we do, we create a dependency graph for all your Java files in that module, and then we levelize that graph. Of course, if you know graph theory, you can only levelize cycle-free graphs. So what do? We basically condense cycle groups into logical nodes. So in this case, we have a little cycle group between F, G, and H. So we just create one logical node out of F, G, and H called FGH. Now, as soon as we have a cycle-free dependency graph, we can levelize the graph. Means the ones that have no outgoing dependencies on level 1, the ones that only depend on level 1 are on level 2, the ones that depend on level 2 and level 1 on level 3, and so on. So that's what we call a levelized graph. And now we can actually calculate what we call fan-in numbers for those nodes. Means on what percentage of higher level nodes does a lower level node depend? That's what we call fan-in ML, fan-in maintainability level. For example, for A, that would be 3 nodes. A is used by E directly and by I and J indirectly. So it would be used by 3 of 8 nodes from the higher levels. So its fan-in ML would be 37.5%. For B, you could say it will be used directly or indirectly by FGH, obviously, and then by J, K, and L. So it would be used by 6 of 8 possible nodes of the higher level. So it would be 75%. So B, C, and D would all have values of 75%. FGH also would have values of 78% because they're used by J, K, L. That's all 3 of the 4 nodes on the highest level. E would have a 50% value because it's used by I and J, 2 of 4 nodes on the higher level. Now you create the average of all those fan-in values, and then you say 100% minus this average to get to the value, to the first version of maintainability level. So that's this line here. That's very simple. And what we notice, one thing is important to notice here. If you go to the higher level here, to the highest level, we have no incoming dependencies. All nodes on the highest level have an fan-in value of 0. So of course, we want to have as many nodes on the highest level as possible. Means we want to have as many nodes with no incoming dependencies to get better values. And that's where you should put all your complex functionality. So the complex business logic should be on the highest level. That would be good, because if it doesn't have incoming dependency, you can change it without affecting anything of the rest about your system. But then you wonder, how the hell should I call this functionality if it doesn't have any incoming dependencies? I can't use it. Not totally true, because the trick is to encapsulate your functionality by an interface. So people only call that interface. That interface is on a lower level. They can call that interface, and the implementation is completely isolated over the interface. That's how you get better values of maintainability level. It's always a good idea to have your functionality in the highest level with as little incoming dependencies as possible. Yeah, vertical slices are helpful because they basically also decrease dependencies between those vertical slices, which is good. And that is also important if you want to achieve domain-driven design. And domain-driven design is basically the precondition to create something what we call the modulith. The modulith would be a modular monolith. So monoliths by themselves are not bad. Of course, big ball of mud monoliths are very hard and hard to work on. But if you keep the structure nice, a monolith can be a good solution for what you want to do. Then we add some additional stuff in the metric, which is, I have an article about it. I will put the link up in a second, where we have all the details about the implementation, but basically we add some penalties for cycle groups. And you can read about this right here, because we had to do some fixes to the metric, because this metric by themselves wasn't perfect yet. And we had to add some alternative calculations and some special tweaks to make that metric work for almost all cases out there. So the details are in this article here on the blog.hellotomorrow.com. You will find it if you look for maintainability level, or this title here, promising new metric to track maintainability. I'm going to jump over that because we run a little bit out of time now. We have another metric is interesting to measure local complexity. It's called cyclomatic complexity, and basically tells you how many different paths could I use to step through a method or through a function. And that is equal to the minimum number of test cases you would need to get 100% test coverage for that method. So different ways to calculate it. One way, the traditional way, is you create a flow graph of your method, and then you say the number of edges minus the numbers of node plus 2. In that case, this one has a cyclomatic complexity value of 2 in that case. But you could also use something very simple. You can start with a value of 1 and add 1 per decision point, per if statement, per while, per for, and so on. You get that increases cyclomatic complexity. And of course, we want to keep that metric reasonable. This is actually a very well-researched metric. So we know that if values go over 25, the error probability grows exponentially. So a safe threshold would be something around 15. Some people are much stricter about it. I'm not a big fan of keeping it under 15. You should keep it under 15. Some people say 7 is a better threshold. I think that's a little too strict. What do you do if your complexity goes over that value? You split up the method. You basically split it up into several methods to make sure that they all stay readable and controllable. The different variants of cyclomatic complexity. There's one special version called modified cyclomatic complexity, which only adds 1 point per switch statements, because otherwise switch statements would be at 1 point per case. And sometimes that can mess up your metric a little bit, because switch statements are tend to be not as complex as if and for loops. And then we have extended cyclomatic complexity, which also adds 1 per logical and or condition. So if you have something like if A greater than 5 and B greater than 0, then you have basically another if statement in your computer, because the compiler will short circuit those things. Then, of course, you can average the complexity. So this measures complexity for a single function or method. Of course, what you want to know at the end is how complex are my classes, or how complex are my packages. And basically for that, you can create weighted averages. And the weighted average basically is better than just a normal average. Just to justify that, just think about a class that has one very long and complex method and 100 setters and getters. Yeah? So setters and getters just have a cyclomatic complexity of 1. If you just use a normal average, that would basically water down that complexity quite a bit. But if you use the number of statements also as a weight, you can have a much better average value. So we use the number of statements as weights for complexity. And then we get class complexity, package complexity, module complexity, and so on. Another good indicator of complexity would be max indentation depth. So how deep do you have to indent your code? If you have an indentation level of 5 or 6, probably your code is too complex and you want to do something about this. So it's another good alternative indicator of complexity. And I would say in my company, for example, we say that complex methods are the ones that either has a cyclomatic complexity of bigger than 15 or an indentation depth of greater than 4. Then there's another method called lack of cohesion of methods, version 4, that basically tells you how many, that is a measurement for a single class, because we want maximum cohesion within one class. That means one class should work on one purpose, means all fields and method of this class should work together. Means the ideal value of that would be 1. We have one cohesive group. How do you calculate that? You build a dependency graph for the fields and methods in your class. We can do a simple example here. Again, another thought experiment. Let's assume we have a very simple, stupid class with 2 fields A and B and 2 getters, get A and get B. In this case, get A would depend on A and get B would depend on B, but we had 2 independent dependency graphs in that class because A and B world basically do not talk to each other. In that case, we would have an LCOM4 value of 2, which means we could split technically this class into 2 classes without any side effects. So this metric comes with a grain of salt. It doesn't work well with inheritance hierarchies. There's some special rules how overwritten methods have to be counted and so on. Works best with classes that are directly derived from object. Now, another cool thing you could do for software visualization is using what we call software city view. That is a simple trick basically to visualize your software system in a way that you can look at 2 or 3 metrics at the same time. For example, this little visualization is basically based on Apache Cassandra. Each building is a Java file. The footprint means that the area of the lot of the building is proportional to the lines of code, and the height and color can come from 2 different metrics. In that case, the height was derived from complexity, average complexity, and the color was derived from how often was it changed in the last year. So what we're looking for in this graph would be tall red buildings, because those are complex files that are changed frequently. So they're what we call bug generators, because if you have a complex file that is frequently changed, chances are that you will add new problems when you change it. Last metric today would be component rank. It's basically based on the PageRank algorithm of Google. You could do the same thing that you do for PageRank for the classes in your system. And basically that tells us how likely will you, when you're reading the code, how likely will you end up on a certain class. It's calculated in a very simple way. So like the Google PageRank, basically you start picking a random class in your system, and then with 80% probability will follow a link to another dependency to another class. With 20% probability will stay at that class. That's where I stopped reading my code. And then you run this algorithm 1 million times or something like this, and you can end up with some probabilities. The probabilities add up to 100%. And why is this metric useful? It tells us when you are unfamiliar with a certain piece of code. Let's assume you have you get a new job and you have to understand the code base of a system that you're supposed to work on. How do you start reading the classes? You start reading the classes with the highest component rank first, and then work your way down the list if you want to understand the code base. That's why this metric can be useful. Now, how do you avoid the big ball of mud at the end? So some very simple rules. Avoid package cycles. That's one of the first things. Then if you have class cycles, make sure that within the same packages I have not more than 5 elements. Keep your maintainability level above 70%. That already, just by following those rules, I can tell you that you will be better than 90% of all systems of comparable size and complexity. Then bonus rules, also very helpful. Avoid complex methods and avoid large classes. There's a book out there And I proudly wrote one chapter of that book. It's a 10-chapter book about software architecture metrics. And if you want to go into detail, most of the metrics I explained today are also in the chapter of this book, which I wrote. Okay, and we came finally to the end, just in time. We have 4 minutes left for question and answers.
Great. Thanks a lot, Alexander, for a brilliant session. Just to kind of highlight 2 things, one thing is, the thing about indentation, right? That's something that most programmers or architects can easily figure out. I think, those are, some of those easy things. But I think, like you showed, dependencies are a complex and multi problem, and then, you will obviously need tools, and then we've really seen how some of these mistakes that we make every day, right? So most of us are guilty of making these mistakes. So brilliant session, really sort of grounded the whole thing, put that focus on this area. So thanks a lot. And I have some questions that came to me separately. So one is we have to prioritize between doing chunks of small code versus slightly longer code. What would you prefer? Because if you have too many chunks lying around, does it make it more complex from a maintainability standpoint? Or do you prefer some sort of if not a very monolithic thing, some sort of a consolidation?
So that's again, the answer would be it depends, but I think there's a fine balance here, because of course you can reduce local complexity by have a lot of short methods, but then of course you make reading harder, because basically the context is split over many methods. That's why there's a fine balance. Again, that's where the metrics can help. That's my threshold, as I said, would be around 15 cyclometric complexity, where I start splitting methods. So that is a good compromise, because if you're at 15, you still usually can keep the method on one screen in your editor. So it makes it easy to read. As soon as you have to scroll very far and scroll down to read the whole method, it's probably too long. So as long as the content of your method can fit on one screen in your editor, it's okay. As soon as you start scrolling, I would think about splitting stuff up. So that's my personal feeling about that.
Got it. That's great. And then the other question that I have is, do the tools also have the functionality to not allow committing to a repository if it doesn't meet certain architectural standards? Or are those use cases enabled by these tools?
So the use cases, so SonarGraph Explorer, the free tool, has the use case where, for example, can break the build if cycle groups get bigger than a certain size, or you can totally break the build if any cycles are in there, and can also break the build based on metric thresholds. So that's possible with the free tool. There's a commercial version of SonarGraph Architect. It's basically the same download, but the commercial version also does those 3D visualizations, which we saw at the end, and it also comes with an architecture DSL, with a domain-specific language to describe architectural rules, so that can give you more possibilities to break the build. But if you just follow the basics that I recommend here, you can totally work with the free tool, SonarGraph Explorer. And it also comes with a free build tool, which you can integrate in your build and determine when you want to break the build based on the capabilities of SonarGraph Explorer.
Got it. So that's pretty helpful too. Thanks a lot, Alex, once again, for taking the time out to do this session with us. I think top of the hour, on behalf of the entire team, the entire Starof community, would like to express my gratitude for doing this session with us, and we hope to bring you back again for another edition sometime soon.
I'd be honored, and I'd come anytime you ask me. Okay, thanks a lot. Bye bye.
Thanks a lot. Yeah, bye.